Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome back everyone. This is the third tutorial in the emerging topic section, and it's the tutorial on high-performance hardware for machine learning. So in the following 2 hours, Bill Daly will survey the state-of-the-art in high-performance hardware for machine learning with an emphasis on hardware for training and deployment of deep neural nets. So it's kind of a continuation of what we've seen in the morning by Jeff. Deep neural nets have an amazing popularity, as we can all see here in this conference, not the least due to the efficiency with which they can be trained on GPUs. I think Bill's going to talk about that. So GPU implementations of deep neural networks make substantial improvements over the CPU-based implementations, and in this tutorial, Bill will also discuss some general observation about the relative importance of arithmetic and memory bandwidth in dedicated hardware for general machine learning tasks. So a few words about Bill before we get started. Bill is the chief scientist of NVIDIA and a senior vice president of NVIDIA Research. He joined NVIDIA in 2009 after 12 years at Stanford University, where he was chairman of the computer science department and the Willard R. and Ines Kerbel Professor of Engineering. In fact, he's still at Stanford, 1 day a week. At Stanford, Bill and his team developed the systems architecture, network architecture, signaling, routing, and synchronization technology that's found in most of the large parallel computers today. Bill was also at the MIT from 1986 to 1997, where he and his team built the J and the M machine, experimental parallel computer systems that pioneered the separation of mechanisms from programming models and demonstrated very low overhead synchronization and communication mechanisms. From 83 to 86, he was at Caltech, where he designed the MOSIMS simulations engine and the Torus routing chip, which pioneered wormhole routing and virtual channel flow control. Bill is also a co-founder of Valio Communications and Stream Processors. He's a member of the National Academy of Engineering, a fellow of the American Academy of Arts and Sciences, a fellow of the IEEE and the ACM. He received the 2015 Funai Achievement Award from the Information Processing Society of Japan, the 2010 Eckert-Matchley Award, which is considered the highest prize in computer architecture, as well as the 2004 IEEE Computer Society Seymour Cray Computing Engineering Award and the 2000 ACM Morris Wilkie Award. He received bachelor degree in electrical engineering at Virginia Tech, master's degree in electrical engineering from Stanford, and a PhD in computer science from Caltech in '86. That's a long list of achievements. One thing that I haven't mentioned is in his spare time, Bill does not work on hardware, but Bill does work on images. So he's a very avid photographer, and here you see some of the photography that Bill is doing when it's in spare time. So it's an impressive picture, but I found that one even more impressive. And so with those images, let's welcome Bill to the stage.
Well, thank you, Rolf. It's a real pleasure to be here. By the way, you need to have somebody generate all those images for the next version of the ImageNet competition. I really find it exciting to be talking to the deep learning community because I find that the deep learning community has a lot of the excitement that the hardware community had back in the 1980s when things were moving very quickly. I see people put papers up on arXiv, and within a week, people are starting to code their own version of it and getting some results and building on the work. That's just a very exciting environment to be in. I think a lot of the reason why it's so exciting, and this was sort of mentioned in the sort of Jan LeCun and Yoshio tutorial this morning, is the ideas in deep learning have been around for a long time. When I was a graduate student at Caltech, I took a course with John Hopfield and learned all about neural nets at the time and Hopfield nets. And convolutional neural networks have been around since Jan LeCun's paper in the 1980s. Most of the ideas that we're deploying today have their roots no later than the early 1990s. And the reason why it's taking off now, it didn't take off then, is really twofold. First, to make deep learning really work, you need to have a lot of data to train on. So put a mouse here. So you need things like the ImageNet data set. Without having sufficient data, you can't train a big model. You'll overfit and you'll get really poor results. But the other factor is you need really good computing. The computing horsepower you needed to build realistic deep learning systems simply did not exist in the 80s and 90s. So it was great that all the foundational work was done there. So now that we have hardware, we can move forward. there's a real need for speed in deep learning, and I thought it was really captured well in this paper by Lavin and Gray. I took an excerpt out of it here, where they basically point out that if you have a large data set, then you can build a bigger model because you basically have a model with more capacity if you have more data to train it with. And then if you have a bigger model, you need more need for compute. And in particular, if you're deploying this in a real-time application, for example, for driver assistant in automotive, you also are latency constrained. And this means two things. One is there's a huge premium put on getting the task, whether it's classification or detection, done very quickly. But also, you can't batch the problem. You can't try to make the problem easier by queuing up 8 or 64 images and then running them as a batch to turn your matrix vector multiplication into a matrix multiplication. You have to run very fast with a batch size of 1. And one final point I'll make on this slide is, for years when people had a need for speed, they could just wait, and the next processor from the big CPU manufacturers would solve their problems because Moore's law was giving you huge gains every year. That's over. The real performance you get out of a process node of technology is probably around 1.1 to 1.2x. So you're no longer getting that 2x per generation that you got at one point in time. But we still have this need to build bigger models and run on larger data sets. So I'm going to talk a little bit about how we're going to address that need. Here's an outline for the talk. I won't read it to you, but you'll see this slide at the beginning of each section. The first section is really to try to define the problem we're solving and set up a nomenclature for the rest of the talk. So the problem really has a couple aspects to it. The first is we'd like to run faster. This is whether it has to do with being able to run a driver assist program real time, which might mean a latency of no more than 30 milliseconds or so. Or maybe I simply want to train a large network in a few days rather than months. But very often, in addition to just being faster, I want to be more efficient. And efficiency has two dimensions. Very often, particularly in data center applications, we're really limited by power. The amount of computing we can put into a rack is limited by how much I can provide power to that rack and cool that rack. Very often 20 kilowatts or 30 kilowatts per rack. So in a very real sense, a measure of goodness of a deep learning application is inferences per joule, or inferences per second per watt, if you prefer to mix the units up. And that really determines how much I can get done on a certain power budget. Also, very often we don't have infinite financial resources, and I'm interested in inferences per second per dollar. I'll also talk about a couple related problems. If all I'm doing is inference, that means running the network forward. I'm presenting an input. If I'm doing a computer vision application, the input will be an image, and I will get an output, perhaps a detection. That's simply running the network in one direction. But before I could deploy that network, I had to train it. And for training, I need to do two things. One is to run the network forward, but then I need to take the loss function that I get and propagate the gradients backward through the network. It turns out that computation is almost exactly the same as the forward computation, but running in reverse. But I'll talk about the nature of those computations. And then as I propagate that gradient past the weights, I want to take the partial derivative of the gradient with respect to the weight and update the weights with that. So there's a weight update, which can wind up being a bottleneck for training if it's not done carefully. And then there's the question of what type of network we're running. So if I'm running a fully connected deep neural network, something that looks like this, I want to run one type of operation. In fact, for this type of network, the critical operation is to do a dense matrix times vector multiply. So the way to think about it is for each layer of the network, say I'm on the input layer, I will consider that for this layer my input activations. For every output of that network, the output activations, I will have a weight for each input. So in a typical fully connected layer, like the fully connected layers in AlexNet, there are 4,096 input activations, 4,096 output activations, and 16 million weights. And for a single inference moving forward, that fully connected layer will basically do a matrix vector multiply. I'll take the 4K input weights, multiply them, basically doing a dot product of the input weights with each row of this matrix, and the results of each of those dot products give me one of the output weights. So a 16 million multiply matrix vector multiplication. Now, after I've done this for one layer, my output weights become the input weights of the next layer, and I just do it over again until I've done all of the layers of the network. And if I'm Doing training, I then do the same thing backwards, where once I've computed a gradient at the output weights, I basically apply the chain rule to compute the gradient at the input weights, summing the contributions of each of the output neurons multiplied by their weights to get the input neurons. It's just a matrix vector multiplication again, except now the vector is gradients rather than activations. It's the same weight matrix. And I also need to produce the partials with respect to the weights for weight update. Typically, if I'm not worried about real-time constraints, I will batch this problem. By batching, I mean that I will take many images and put them all together and run them through the network as a unit. And the reason I do this is to get reuse out of this matrix. If I do matrix vector multiplication without batching, I basically have to fetch this entire matrix. It's 16 million weights. It's too big to fit in the cache of modern CPUs or GPUs. So I basically have to fetch this entire matrix, and I use every element of that matrix exactly once. I multiply, Wij by Aj to produce Bi, and then I'm done with Wij. I don't touch it again. So I have a ratio of one word loaded from memory for each multiply. And that's horribly mismatched to modern computer engines, which typically want a ratio of more like 10 to 50 arithmetic operations per word loaded from DRAM. So to get that ratio up, we will typically batch the operations. And now instead of a matrix vector multiplication, I've turned both the forward and backward steps into a matrix multiplication. And I get a reuse out of this matrix that's equal to the narrow width of this matrix, which is here K, the batch size. But in real time, I can't batch. So I'm back to doing a matrix vector multiplication. Moreover, if I'm really trying to optimize my system, and I'll talk a little bit more about this later, I will exploit sparsity. There's sparsity in both the activations and in the weights. The sparsity in the activations comes, and I'm showing it the reverse direction picture here, but in the forward direction, after I've done my matrix vector product, I apply a nonlinear operator, very often a rectified linear unit. And that rectified linear unit, because it clips off the bottom part of the response at 0, I'll typically have something on the order of a third to 2/3 of the activations to be 0. And so it would be a horrible waste to do 3 times as much work as I needed to do by multiplying all of those zeros. So I can exploit sparsity by only multiplying by the weights that are only by multiplying by the weights that are non-zero. I'll also show later in this talk how it's possible to prune the fully connected layers to remove about 90% of their weights. And this is true both for networks like AlexNet and VGGNet for images, as well as for networks like NeuralTalk for dealing with natural language processing. And as a result, I can eliminate another 10x of the work that needed to be done. So if I'm really worried about efficiency, this isn't a dense matrix times dense vector operation. It's a sparse matrix times sparse vector operation, which is among the hardest operations to do efficiently because there's irregularity there. The irregularity on the vector side is actually dynamic. I get a different set of non-zeros in the vector every image, and the irregularity on the matrix side is static. Once I've pruned the fully connected layer, the non-zeros in the matrix remain, the zeros in the matrix remain zeros, the non-zeros remain where they are. So that's for the fully connected layers of a network. And for the recurrent neural networks we see for speech, for a lot of the natural language networks, they're essentially all fully connected layers. Even for convolutional networks for images, the fully connected layers are very important. The bulk of the arithmetic operations actually happen in the convolutional layers, but the bulk of the memory operations happen in the fully connected layers, and very often we wind up being memory limited, especially with a batch size of 1. Also, there's a move today to basically run the convolutional layers at the front end of networks like AlexNet and VGGNet once, and then run multiple detections on the back end repeatedly using the same set of features that were learned by running the conv layers once on many sets of fully connected layers for different detections. But the convolutional layers are also important, and so for the image nets, we tend to run the first several layers as trained feature detectors. To me, this is really revolutionary. I have colleagues who spent their entire career sort of designing hand-tuned feature detectors for different computer vision problems, and all that work is now completely obsolete because neural networks just completely outperform all of the hand-tuned feature detectors across the board on computer vision problems. And what the work is to do here is we take a piece of our image and we basically multiply it by a kernel, essentially taking a dot product of a 2D chunk of the image by the kernel, and then that produces one pixel of a feature map. I will typically, after the first, let me pop back here, typically after the first layer, I will have a number of different feature maps. Very often these are called channels. When I do my next convolution, I basically do a convolution, it's really a 3D convolution now, by X and Y in the feature map and Z over the channels by a filter to produce an output feature map. And as I get deeper in the network, while the X and Y dimensions, these feature maps tend to get smaller, I tend to have more parallel feature maps, more channels that are done in parallel. And I get down to the point where I have the last fully connected layer, and then I basically drop into a set of, last convolutional layer, and I drop into a fully connected layer to do the classification on the set of features that I just learned. So in addition to the matrix times vector multiply, which is the key operation of the fully connected layers, the other key operation that we need if we're doing a convolutional network is doing convolutions. And basically just doing this convolve of a kernel over the input image. And I'll talk about later in this talk about how very often before you accelerate things by trying to throw great hardware at it, it's important to make sure you're using the best possible algorithm. A brute force convolution requires a number of multiplies equal to the non-zero support in the convolution kernel. So if I have a k by k kernel here, I basically have to multiply every, to compute each image point, I have to multiply k by k points of the input image by the kernel. And so I wind up doing k squared multiplications for each point in the output map for each output map. I'll talk about later how by doing transformations before doing these multiplies, I can reduce that k squared multiplications to one multiplication. But for now, let's continue thinking about the brute force approach. If we do the brute force approach, this convolution is really a 6-dimensional loop. So basically, the dimensions are the output maps, since I have some number of channels of the output, and the input map, since I have some number of channels of the input. And then I have each pixel of that input map, x, y, and then I have each element of the kernel, uv. So I basically have a 6 deep nested loop, at the very bottom of which I'm doing a multiply and accumulate of that kernel. So this is computationally very intensive. It tends not to be as memory intensive because I'm sharing the weights. In the fully connected layers, I'm fetching each weight, unless I'm batching, I'm fetching each weight and I'm using it for one multiply. Here I can fetch a kernel of weights and then scan it over the entire input image. And so I wind up being able to reuse that weight, basically multiplied by the size of the input image. So I wind up being multiply limited in convolutional layers, whereas I'm typically memory limited without batching in the fully connected layers. For speech networks and certain natural language processing networks, we see a lot of recurrent neural networks. And these are really just fully connected layers where we've folded them back on themselves. So that basically for each of the elements of this recurrent layer, in addition to having connections from the preceding set of activations and the next set of activations, they have connections back to themselves via a set of activations that basically form a short-term memory for the network. But for the sake of the processing demands, the hardware requirements of doing recurrent neural networks, they're basically no different than doing a fully connected layer. Now we do need some other operations to plug our network together, but they tend to, you need to be able to do them and not have horrible performance on them, but they tend not to be limiting. The first is a pooling operation, where very often in the convolutional stages, I'll reduce the size of my input filters from one stage to the next by taking 4 adjacent pixels that I've computed and, for example, taking the maximum of them if I'm doing max pooling. So I have to be able to efficiently pool my network, and this lets me reduce the size of the image from stage to stage and gives you a certain amount of location invariance in your feature detectors, since detecting a feature in any one of these 4 quadrants will give you the same response in the next set of channels. Typically, after pooling, I'll do a nonlinear operation where I will apply, for many years, people would use a hyperbolic tangent or sigmoid operation here because that was thought to have all sorts of great properties. And then at some point in time, people started using ReLU and found that it actually worked better. And ReLU is really easy to implement. It's basically, if your input is less than 0, output 0. If your input is more than 0, output your input. Many people will do a clipped ReLU where they'll also put a max on this. So it'll actually be 0 and then a unit slope up to the maximum and then at that maximum for a certain point in time. And then if I'm training, I also have to update the weights. And this winds up being a critical operation simply because there are a lot of weights. You may have, for a complex network like VGGNet, several hundred million weights. And so you need to manage the memory to be able to update these without exceeding your memory bandwidth. If you accelerate everything that goes on in the neural network itself, very often you'll find that some other part of your overall data center system or embedded system, if this is an embedded application, will be dominant. So for example, if I'm doing image training, I have to make sure that I can fetch the images from whatever storage they're on. If the images are on disk, I have to be cognizant of what the maximum bandwidth of the disks are, or that can become a limiting factor. Very often people will actually store them in DRAM spread over the data center to avoid the disk access. I then have to decompress them. So for example, if I want to classify this eagle image here, this is an eagle plucking a fish out of the water, it'll start out in JPEG form. And I have to make sure I have enough decompression compute capability to decompress my training images, because I'm not going to store them in decompressed format. It takes way too much storage for that. So I have to decompress them. Then I'll do the acceleration of the deep neural network, and then I'll produce an output. Maybe this was like the neural talk network where I'll label the image, eagle grabbing a fish from water, and I'll have to do something with whatever the output is. And so if you do a really good job at this box, it then often creates problems for you doing a good job at the rest of the things in the data center. But that's a high-class problem to have, and for the remainder of this talk, I'm going to concentrate on the box here labeled DNN and assume that you've done a good job with the rest of the infrastructure. To sum up the problem we're solving, our goal is to be able to run multiple types of deep learning networks, fully connected deep neural networks, convolutional neural networks, and recurrent neural networks, and various combinations of the above for both training and inference in both latency and latency insensitive ways. And we'll be able to batch if we're not latency sensitive. And I want to optimize both speed, because if I'm a developer, very often what I'm concerned about is I'm trying to develop a new network. I'm experimenting with a lot of different hyperparameters. I don't want to have to wait a month to find out if my great idea on these hyperparameters gave better accuracy or worse accuracy than the old way of doing it. I'd like to get that turnaround in at most a few days. And also efficiency, because ultimately in the data center I'm limited by the cost of the installation and by the energy it takes. The key operations I need to accelerate are matrix times vector for the fully connected layers. If I can batch, I will turn that into a sort of tall, skinny matrix times matrix, basically a square matrix times a tall, skinny matrix. And if I can't batch, it will remain a matrix by vector. And if I exploit the sparsity, both the dynamic sparsity of the activations and the static sparsity of the weight matrix, it actually turns into a sparse vector times sparse matrix operation, which leads to a lot of irregularity that I need to deal with. For the convolutional networks, I also need to do convolutions, either with the brute force k-squared method, or as we'll talk about later, with one of the transform-based methods. It basically reduces that to basically a single multiplier per image point. And then between the layers, I also have to do things like pooling and nonlinear operators, and for training, I need to do weight update. So let's start out by setting a baseline. If I was simply to take an average data center machine and load Caffe on it and use the Intel deep learning framework, what kind of performance will I get? So this is the baseline against which I'm going to measure everything else in this talk. A single processor of a Xeon E5 2698, and that means absolutely nothing to me or to anybody else, I'm sure. But what this is it's sort of a standard Intel data center processor. This is a hexadecacore processor, as Intel refers to it on their webpage, which means it has 16 cores. I'm going to use just one of them, run Caffe, and I'm going to get 30 frames per second and 3.2 frames per joule, basically frames per watt second. Now, I will point out is if you actually ran this on just the CPU, it would be an order of magnitude, actually maybe more like a factor of 30 worse than this, in both performance and in energy per frame. And the reason is that even when you're just running on the CPU, CPUs are horribly matched for this job. But the AVX units, the SIMD units on the CPUs, do way better than the CPUs do on it. So actually most of the ops, if you're running Caffe or one of the other deep learning frameworks on a CPU, are not happening on the CPU itself, but are happening on the SIMD units. Now a lot of people would say, well, I'll just wait until next year and buy another chip from Intel if this isn't fast enough. And for many years that worked, but it doesn't work anymore. And I give whole talks about the end of Moore's Law, and I don't have time in the 2 hours here to do that. But I'll sort of summarize a lot of what is both the end of Moore's Law and the end of what's called Dennard scaling, which is really what's led to the end of performance scaling for CPUs. With this slide, which was presented by Chuck Moore. Moore's Law is due to Gordon Moore, who was one of the founders of Intel. Chuck Moore actually died a few years ago, but before he died, he was CTO of AMD. And he presented this slide at the Salishan meeting in 2011. And what it shows is scaling of CPUs in a number of dimensions from 1975 to 2011, which is when the slide was done. And what you'll notice is during this, the really important curve here is the blue one, because that's performance on SpecInt, which is actually a pretty good proxy for things like neural networks, so the SpecFP would probably be a little bit better. What you see is that from 1990, where you got about 100 SpecInt out of a single CPU core, to the present, roughly, say 2010 on the slide, because it's pretty much flattened out, where you get about 30,000 SpecInt, you got a factor of 300 in 15 years. In fact, you got most of that 300 you got about 100 in 10 years, and then a factor of 3 in the following 10. A factor of 100 in 10 years is not going to happen again. We're now over 10 years going to get maybe a factor of 2. So we're not getting the performance that we got at one point in time. I will point out that the number of transistors per chip is still going up. That's actually the top line here. And that's what the original Moore's Law was all about. The popular version of Moore's Law, though, is really about this blue line, which is about performance. And the reason why it's not going up the way it used to is because while the original Moore's Law, the number of transistors per chip is still scaling just fine, the popular version of Moore's Law really depended on something called Dennard scaling, which basically reduced voltages as we made the devices smaller. And that allowed us to get more energy efficiency building the same thing in a smaller process technology. We no longer scale voltage with process technology the way we did up until about 2005. You'll notice that's when a lot of things start to flatten out here. And because of that, the gains we get going from one generation of process technology to the next, which used to be about a factor of 3 per generation, a factor of 8 over 2 generations, which is cutting the linear dimension in half, is now more like a factor of 1.2 per generation, and perhaps a factor of about 1.5 over a pair of generations, cutting the feature size in half. So without Moore's Law, how are we going to continue to scale the performance we need to basically build even better deep neural networks? As we get larger data sets, we're going to want to build networks with more capacity to be able to train with those data sets and to get even better accuracy and to tackle more challenging problems. So I'm going to go through, for the rest of this talk, a bunch of ways of doing that. The first is how to do things in parallel. Then we apply our silver bullet of GPUs. We'll talk about reducing the precision of the computation, compressing the networks, using better algorithms, and then finally, at the last resort, going to special purpose hardware for deep neural networks. So the first rule is if you want to go faster, use more processors. If you look at the problem of computing and inference for a deep neural network, it is what the parallel computing community refers to as an embarrassingly parallel problem. Well, I don't get embarrassed by very much, so I just refer to it as an easily parallelizable problem. I don't find it embarrassing at all. We have many dimensions of parallelism here. We have parallelism over the input set. This is what's often called data parallelism. If I have a large training set, I can basically run different GPUs on different images in parallel, and I simply have to combine the weight updates at some point so that they learn from what each other has seen. Points in a feature map. I've got a large input image here. I can dice that input image up and have different CPUs or GPUs work on different parts of the input image, or more accurately, you really want them to work on different parts of the output feature map for their layer. But it's a very local computation, so to compute, say I quarter my output feature map here, I basically quarter my input feature map, but I have a little halo hanging over each one of those that has to be shared between the processors that are working on that. When I get to the fully connected layers, I have 16 million multiplies that are completely independent. So if I had 16 million processors, I could do those all in parallel. I would then have a tree reduction to do with the summing them up to get the output activations. In fact, the only data dependencies here are from layer to layer. I have to compute one layer before doing the next. But if I don't care about latency, if I'm doing training, or if I have a latency insensitive inference task, I can even pipeline over the layers, which is another form of parallelism. And there's no data dependent operations until I start to exploit sparsity. So in fact, it's an entirely static computation. I can spend lots of time at compile time and schedule this all completely deterministically before I start the computation, because there's no if statements in here that are based on stuff. So the first approach is data parallelism. It's by far the easiest to do. You train on one GPU and it takes you a week. You want to get down to 3.5 days. You basically buy 2 GPUs. You take half your data set and run it on one, half your data set and run it on the other. Now, these aren't 2 completely separate computations because I need to share the weight updates. And so I'll take my mini batch size, say I do a mini batch size of 256, and I'll run 128 down each pipeline. And at the end of that mini batch, I have to share the weight updates from one pipeline to the other pipeline, so they've all learned the same thing. Even though they only saw half the images, they've learned from both halves of the images. And I can continue this. People have successfully applied data parallelism up to 128 GPUs, and I'll show you some data on that in a few slides. This doesn't affect the latency for any one input, but it does require a p-fold larger batch size. So if I'm exploiting p-fold parallelism, if I have p GPUs working in parallel, and I need, say, a minimum batch size of 8 images to make each GPU work efficiently, I now need 8p images in my mini batch size. So for example, if I want to run on 8 GPUs and my mini batch size is 64 images, I'll be running 8 on each GPU, and that's still a pretty efficient operating point. And then for training, I need to coordinate the weight update. So across these different ones, after I do my back propagation on each mini batch, I have to take my weights and exchange them. And there are 2 ways to do this. This is a figure from Jeff Dean's paper from 2013 on large-scale distributed deep networks, where they use the notion of a parameter server. There's one server in their network that's responsible for all the weights. After each forward and backward step with a mini batch, each of the workers, think of that as each of the GPUs working on a part of the data set, sends their delta parameters, their change in weights from the gradient back propagation over that entire batch up to the parameter server. The parameter server gets everybody's deltas, adds them to the weights, calculates the new weights, and sends them back to everybody. And you can do this in a slightly asynchronous fashion. So rather than having these workers wait for the update before they start on the next go, they can start on the next mini batch and basically be slightly out of sync. And there's various effects of that on your learning rate, but most people will do an asynchronous update here. Some people will insist on doing it synchronously, which has certain complications. The other approach to doing this, you eliminate the parameter server and you simply exchange the weights directly between the model workers. And very often you'll, for example, connect them in a ring where everybody will send just their fraction of the delta at the first step of the ring, and then they'll accumulate, send theirs and the one they received on the next, and go all the way around the ring until everybody has received everybody's deltas around the ring. So that's data parallelism, where I split my input training set up and divide it over some number of worker GPUs. The next approach is model parallelism, where and I can apply these 2 together. I can do data parallelism and model parallelism at the same time. But model parallelism is exploiting parallelism within the model itself. And so let's look at how this works in the 2 types of layers. In the convolutional layers, the best way to do model parallelism, if I look at my 6-dimensional loop, is to do it over, you can think of I have 6 nested loops, and I want to take one or two of those dimensions and split them across GPUs, the best dimensions to split across the GPUs are the output map coordinates, what I'm calling XY here. And the reason that's the case is that these computations are entirely independent. So I can compute the green region of an output feature map completely independent of the red region of the output feature map. And they also are relatively local in the input data they use. The red region of this feature map uses sort of its area in the input feature map plus a halo, which is equal to 1 less than the width and height of the convolutional kernel, I should half the convolutional kernel within there. So for example, if I have a 3 by 3 convolutional kernel, this halo is of width 1. So I basically need 1 pixel from the other side of the map to compute the red area. But after I've used that level of model parallelism for the convolutional layers, I can continue going. And the next dimension that's worth exploiting is to compute the different output maps in parallel. Here now I need to share data, right? The blue output map needs the entire input data set, as does the red output map. But the output computations are still entirely independent. And I can combine these basically first dividing in X and Y, and then dividing over maps, and get very high degrees of parallelism in the convolutional layers. For the fully connected layers, the right way to exploit model parallelism is to divide up the activations. And in this way, I can basically say I compute the tan activations on one GPU and the purple activations on another GPU. I can split the weight matrix completely. There's no sharing here. And so the heavy part of the data fetch is now split across those two. And all I have to do is distribute the input activations to both of them. But that's a relatively inexpensive thing to do. Remember, I have 16 million elements of the weight matrix and only 4,000 activations. So sending those 4,000 activations to both GPUs is not a large overhead, double the speed at which I do this computation. And then the most effective way of exploiting parallelism is what's called hyperparameter parallelism. Very often when I'm doing a study, I'm trying to experiment to find the right set of hyperparameters. How many layers, what size convolutional kernels, how many hidden neurons in each of the fully connected layers. And you think of this as a parameter space to search to find the optimal network. I want to search this hyperparameter space. What I'll do is I'll have a bunch of trial networks that I think will give me better results, either more efficiency or better accuracy, or hopefully both. And I will run those trial networks in parallel on multiple GPUs. And these are completely independent runs. They may share some of the infrastructure of image decoding and the like. So first let's apply this to our CPU parallelism. And here I'm going to go to a Core i7. This is a consumer CPU, maybe like the one you would find in a desktop PC. And 1 core versus 6 cores in the Core i7, you get essentially linear speed up. And in fact, a good parallelization, we'll typically get very close to linear speed up to a reasonable number of things. This was almost entirely data parallelism, by the way. If you're trying to do model parallelism, though, your results may vary. This is a chart taken from another Jeff Dean paper, this one in NIPS 2012. And what he shows is if you're trying to just get model parallelism, this is machines per model instance, the parallelism, at least what he saw, was quite low. For the speech network, for example, with 40, oops, I somehow managed to go backwards there. The speech network with 42 million parameters, at 8 GPUs, you're going maybe 2 or 3 times as fast. And then it actually gets worse. And this is an example of overhead. We have these neural networks which have enormous amounts of parallelism in them. I should be able to get model parallelism on the level of thousands out of a network. And in fact, I'm already exploiting some of that. This is running, in 2012, it's probably running on CPUs. But if I'm running on CPUs, I'm running on the AVX units. I'm already exploiting the width of those AVX units times their pipeline depth. There's probably a factor of 32 or so parallelism I'm already exploiting in the CPU. If I'm running on GPUs, within one GPU, I have thousands of CUDA cores. I'm exploiting on the order of 3,000 or so parallelism just within the CPU. It's additional parallelism I need on top of that to get multiple going in parallel. So just to sum up the parallelism section of this talk, there's lots of parallelism in deep neural networks. if it wasn't for the overhead, let me pop back to this slide, if it wasn't for the overhead of communicating the parameter updates and sharing the input data of model sharing where I'm doing model parallelism rather than data parallelism, I should be able to get essentially linear speed up to very large numbers of processors. But what you see here is that there is overhead. Sometimes this overhead is fundamental. It's a limit of the actual physical hardware. More often it's actually artificial, and it's basically overhead that's introduced by the programming system that's used. So for example, if the only way I can exchange parameters is by sending a message over Ethernet network, the TCP IP stack is probably the single largest source of overhead. The actual hardware is way faster. And people will typically try to batch up large updates to amortize that enormous overhead of the software stack. That's one reason why if you have, for example, if you're running an 8 GPU system that are all together on one PCIe bus or through a PLX switch, they can actually read and write the memory of the other GPUs doing what's called peer-to-peer without having to go through any system software. There's no operating system call required, and you can get very efficient weight sharing that way. So it's really important when you're trying to exploit parallelism to accelerate deep neural networks, or actually to accelerate any problem, to make sure the way, when you do have to do communication and synchronization between parts of your computation, that you do that communication and synchronization in a way that overhead, and particularly unnecessary software overhead, does not swamp the actual computation. So there's lots of parallelism, 16 million independent multiplies in each fully connected layer, thousands of updates that can be done simultaneously in convolutional layers. And so you can split the model up many ways and exploit a lot of parallelism, and that's actually why we're able to get good speed up on parallel units like GPUs to begin with, but you can go beyond that and split it over multiple GPUs. The easiest way to exploit parallelism is just to break your data set up. If you're training, you can easily split your data set up and train on different examples in parallel, and then share the parameter updates, either via parameter server or by exchanging in a ring or some other topology. And this is largely limited by batch size. The larger the mini batch you're willing to do, the more GPUs you can split your data parallel training over. Very often people will do things like a batch size of 256 divided over 16 GPUs for a batch of 16 per GPU. You can do model parallelism, where you then split the model up over the GPUs, splitting it by layer, the convolutional layers by the regions of the output maps for that layer, and the fully connected layers by output activation. And it's very, very easy to get, say, 64 GPUs working on one problem by basically splitting a model over 8 GPUs and then copying that unit and doing data parallelism over 8 copies of that unit. So let me get to my favorite topic of this outline. You notice it's central, being right in the middle of the outline, which are GPUs. GPUs are just really cool. And so the sort of repeat, from the parallelism session, if you want to go fast, use multiple processors. If you want to be both fast and efficient, use GPUs, and I'll show some data shortly to sort of back up the claim that they're both fast and efficient. And actually, if you want to be really fast and efficient, use multiple GPUs, because I can take all the parallelism tricks and apply them to GPUs as well. So the sort of gold standard for doing neural network training now, and will be until our next GPUs come out, is Titan X, or its Tesla equivalent, the M40, is 3,072 CUDA cores running at 1 gigahertz. This is 6 teraflops of single precision floating point. Just to put this in perspective, I've been playing with supercomputers for longer than I would like to admit. And in the early 90s, there was a really big deal when the machines, on the #1 machine on the top 500 list hit 1 teraflop. At that point in time, 1 teraflop was the fastest machine in the world. Now, roughly 20 years later, you can buy one of these for $1,000 and have something which is 6 times faster than the fastest machine in the world in 1993. I believe that was like a Connection Machine 5, the CM5 at Los Alamos. What's amazing is that machine was like a 5 megawatt machine. This is a 250 watt machine with 6 times its performance. So 24 gigaflops per watt is just an amazing level of efficiency compared to what you can do elsewhere. To put that in perspective, a CPU, if you don't use the AVX unit, is less than 1 gigaflop per watt. If you use the AVX units, they're around 5-ish. I think they're about a half a gigaflop per watt just running on the CPU part of the CPU. This is a Maxwell GM200 GPU. I had a lot of fun with various parts of it. And it's in a 28 nanometer process. And I'll make sort of a comment here about Moore's law. Our previous generation of GPUs, Kepler, so the K20, K40, and K80 are all Kepler generation GPUs, is also in a 28 nanometer process. The Maxwell generation GPUs like the Titan X and the M40 are in the same process. They are almost exactly twice the performance at the same power level, twice the performance per watt with no process change. So Moore's law, the process isn't giving us any more performance or performance per watt, but with GPUs we're able to double our performance per watt over a generation within the same process, and that's why GPUs are able to do so well at this. So if you're doing either inference in the data center or training networks, Titan X is, for the next period of time at least, the right GPU for you. If you're doing Internet of Things or automotive, or you're doing some embedded application where you need to do inference at very efficient power levels in a small space, we build a Tegra line of SoCs. SoC means system on chip. These are not just the GPU, but also the CPU. We have ARM cores, both of our own design and some that are licensed from ARM. So this basically has 256 CUDA cores at 1 gigahertz. It has 8 ARM cores, 4 bigs and 4 littles. I think the bigs are A57s, the littles are A53s. It's a teraflop of FP16, and yes, that's not a typo, and I'll talk when I get to the limited reduced precision part about why that's exactly the right thing for deep learning. 4 gigabytes of LPDDR, that gives you 25 gigabytes per second of memory bandwidth. By the way, I should have gone back on Titan. For things that are memory bandwidth limited, compared to the sort of 50 or 60 gigabytes per second you get out of a CPU, one of the big advantages of GPUs is the 300 gigabytes per second you have to the GDDR5 memory there. And what's neat about this is that it's sort of 10 watt typical power dissipation. This is 100 gigaflops per watt. That's just an astounding level of energy efficiency. And this is actually in a slightly more modern process than the Titan X. It's in a 20 nanometer process. So to sort of justify my comment that if you want to go fast and efficient, use the CPU, this compares the data center processor I used as the baseline, the Xeon E5, to a Titan X. And what you see, and I've shown both for no batching and batching, and this sort of shows why if you don't have the really hard latency constraint, you want to batch things. If I batch, I'm limited across the 16 cores, this is all 16 cores of the E5 to 476 frames per second, whereas I get over 3,000 on the Titan X. So it's about a 7x improvement in performance. And on power efficiency, it's about 4.4x. And I will note that 4.4x, part of the power I'm charging to the Titan here is the power for the E5 connected to it. Even though that E5 is really not doing much other than loading image data sets and firing off kernels on the Titan X. It's actually, if I was just counting the Titan X, the number would be almost twice that good. If I'm doing embedded applications, I'll compare here a Tegra X1 to the Core i7. The Tegra X1, which is a little SoC intended to be embedded into IoT things, actually slightly outperforms at 10 watts, slightly outperforms a Core i7 at about 60. And on energy efficiency, it's more than 10x. It's 11.5x on frames per joule. So you get great both performance and performance per watt out of GPUs. And the reason is that they eliminate a lot of the overhead that's found in CPUs. CPUs basically have enormous amounts of hardware that's all there to handle the problem that when you do a memory load operation, you don't know whether it's going to hit in the cache and take 3 cycles or go all the way out to DRAM and take hundreds. And because of that, they actually, no matter how much work your compiler did to schedule the computation beforehand, they reschedule the computation in hardware at runtime every time around the loop. And that's computationally very intensive and energetically very intensive. GPUs, on the other hand, have exactly the same problem of unpredictable data latency. You don't know whether something's going to hit in the L1 cache or the L2 cache. You have to go all the way up to DRAM. But we handle the problem in an entirely different way. When we basically have a cache miss, we switch threads. We're a multi-threaded architecture. And because of that, we're able to deal with this problem with essentially no overhead. We can have the vast majority of the joules consumed in a GPU go to actually doing the arithmetic operations and essential memory operations. It's actually, almost within a factor of 2 of the total power is going into things that you have to do. You can't do without. And when I get to special purpose hardware, I'll talk a little bit more about that. So once you have one GPU, you may want to ask, how does it do to do more in parallel? So this is a set of data due to Baidu on image recognition from Archive last year. I realize this group was later discredited because they were making too many submissions, but I don't think it affected their speed up results. And what you can see is that they were getting essentially linear speed up, up to 64 GPUs on a single model. And this really had to do, again, as I said before, with batch size. If you ran a really big batch size, it was actually super linear speed up. And this has to do with basically reuse of data. You wind up having to get less memory bandwidth if you do that. But at reasonable batch sizes, even batch size of 256, they were still getting very good speed up, if not quite linear. A more recent result, this is something which is hot off the press. In fact, it may not actually be up on Archive yet, but I was given a pre-release version of Baidu's Deep Speech 2 paper, and they gave me permission to use figure 4 out of the paper. This is figure 4, which basically shows training a recurrent neural network for speech from 1 to 128 GPUs. Oh, I hate it when it does that. But I went way back. Hold on just a second here. No, I actually went forward. Okay. Would figure. So from 1 to 128 GPUs, I'm going to stop trying to use the mouse because it thinks I'm trying to advance slides. From 1 to 128 GPUs, and what you see is that this is essentially linear speed up. It just, no mouse. It's linear speed up. They basically start at taking roughly 2 to the 18th seconds and wind up at around 2 to the 12th. So they're much closer to 2 to the 11th for this network. So they're essentially able to get 128-fold speed up on 128 GPUs. I will say that this was holding the batch per GPU constant at 64 across this. So the batch sizes at the right side of this graph are probably larger than reasonable and will probably adversely affect their rate of convergence. But certainly in the middle of the graph, so that advancing to the next slide, in the middle of the graph, those will still have very reasonable learning rates. So let me summarize GPUs. For training in the data center, inference in the data center, a Titan X is roughly 6 times faster and 4 times more efficient than a top-of-the-line Xeon E5. And I will point out that that's even though it's actually 2 generations of technology back. That GM200 chip in Titan X is in 28 nanometer. The latest Intel server processors are in 14. That's actually 2x in line width is two process generations, and we're still smoking them. For embedded applications, a TX1 is 11.5 times more efficient than a Core i7, and that's 1 generation back in technology, being at the 20 nanometer node. These are both on inference. They're actually slightly larger gains on training. And then if that's not enough performance for you, data parallelism scales easily to 16 GPUs, and then you can use model parallelism 8 ways across that and get to 128 GPUs with pretty close to linear speed up. To put this in perspective, if I run 128 GPUs versus a Core i7 CPU with 6 cores, that's 870 times speed up. And what this does is it turns a month into a little less than an hour. So GPUs are really time machines. They turn months into hours, and there are very few things in life that'll do that. And so, especially if you're doing something iterative, where you're trying to experiment with hyperparameters and find out whether your latest set of hyperparameters works or not, being able to get turnaround in hours is just a huge thing. But we can do better than that. So let's go back to our outline and talk about precision. Up until now, all of the results I've been showing you assume that you do the entire computation in 32-bit floating point. And in fact, you don't need to use 32-bit floating point. That's more precision than is required for the operation. So I can do a lot better by reducing precision. If I reduce precision, first of all, I reduce storage. If I only need to store 16 bits per weight rather than 32 bits, I just reduce the amount of memory capacity I need by a factor of 2, and more importantly, the amount of memory bandwidth I need by a factor of 2. It reduces the energy. Dominant at that is actually the data transfer energy by moving this data around, because I only need to move half the data around, less if I can get down to 8 or 4 bits. And it improves performance. And up to a point, it has little effect on accuracy, and I'll show some results for that. So let's go back to our dense neural network and ask the question, we really have a bunch of different things that we do. We have activations, we have weights, and we have intermediate results when I'm sort of summing the dot product for the activations times the weights. So how much accuracy do I need when I'm doing these sums and when I'm doing the weight updates? And my sort of menu, or if you want to think about the color palette I have to draw from in deciding how to do this, looks something like this. This is sort of the data formats for both floating point numbers and fixed point numbers. And floating point numbers are wonderful things because they have an enormous dynamic range. A 32-bit floating point number has a dynamic range of 76 orders of magnitude, from 10 to the minus 38 to 10 to the 38. It's way more than you need. But what I'll observe is that a 16-bit floating point number has a dynamic range of 9 orders of magnitude. It's the same dynamic range as a 32-bit fixed point number. So if you could do a computation with a 32-bit fixed point number, you can pretty much do the same computation with a 16-bit floating point number. And the accuracy here is basically the quantization error you get by taking an element of the real number line and representing it by one of these number systems. The accuracies for floating point numbers I give in percent because the error you get changes as the scale changes. When I try to represent very small numbers, the spacing between them is very small. So I wind up with, whatever this is, 6 millionths of a percent error in a floating point number, whether I'm trying to represent 10 to the minus 30 or 10 to the 30th. The size of my error scales. It always winds up being 60 parts per billion. Similarly, I have 5/100ths of a percent error with a 16-bit floating point number, regardless of where I am in that range. Not so with fixed point numbers. With fixed point numbers, my error is a half across that entire range, right? Because it's the same spacing between numbers. I don't have an exponent, so the spacing between the representations doesn't change. And so your quantization noise with fixed point numbers gets very large when you get to the low end of the range, and is usually acceptable at the high end of the range, right? So the difference between the two largest numbers in this floating point range is basically about 1 part per billion. The difference between the two smallest numbers in the fixed point range of a 32-bit fixed point number is a half, right? The difference between a real number and what I would round it to is round to nearest. But this is sort of what I can choose from. Float 32, float 16, and 32, 16, and 8-bit integer. And I'll actually be looking at some 4-bit representations as well. I should say there are 8-bit floating point representations. They're actually quite widely used in telecommunications. They're called mu law and A law. I'm not going to look at those for the deep learning applications. So why do I care about precision? Well, I care because the cost of operations and the cost of moving data around is sensitive to precision. And it's really more sensitive to precision than it is to float versus integer. So just to, not to make you go through this entire eye chart, but the difference between a 16-bit floating point multiply and a 32-bit floating point multiply is almost 4 to 1. The cost of a multiply goes up quadratically with the length of the multiplier. The way to think about this is to multiply two 32-bit numbers, I really have to multiply 4 16-bit numbers, which are the 2 halves of each number by the other 2 halves of each number. I have to fill in all 4 quadrants. And so doubling precision quadruples energy cost for multiplies and the area. The cost of doing a 32-bit fixed point mult and a 32-bit floating point mult isn't that different. The floating point multiply is a little bit more expensive because I've got to do some normalizations and an exponent computation, but I'm actually doing a slightly smaller multiply. I'm doing a 24-bit multiply on the mantissa rather than the 32-bit multiply for the fixed point. The cost of add is very different between fixed and float, but the adds are all relatively cheap, so it really doesn't matter. What really dominates the cost energetically for the arithmetic are the multiplies. And the areas here are slightly larger. That's actually almost about 2x for float versus fixed. But again, that's not usually what's limiting me. The area, as we'll see, is actually not dominated by these arithmetic units. It's also really important when you're looking at the advantages of reducing precision to reduce precision to be able to get a larger effective working set in a certain size memory. Because there's a huge advantage to capturing a working set at some level. So if I can capture my working set in an SRAM that's right next to my arithmetic units, that's huge because fetching a 32-bit word out of local SRAM is only 5 picojoules. And it goes up in order of magnitude at each level of the memory hierarchy. So fetching it from on-chip SRAM, but 8 millimeters away on chip, costs 50 picojoules per word, exactly an order of magnitude higher. And by the way, just to remind you, doing the multiply you're going to do when you fetch this is only 3.7 picojoules. So just fetching it from a local SRAM is more expensive than the multiply. The cost of data movement is huge compared to the cost of arithmetic. In fact, for almost every computation, the cost of data movement trumps the cost of arithmetic. Arithmetic is almost in the noise. And if I have to go off chip to get this, even with an LPDDR DRAM, which is the energetically cheap one, it's 640 picojoules, so more than two orders of magnitude higher, about a factor of 200x over the cost of doing the multiply. And that's doing a 32-bit multiply, by the way. The 16-bit multiply is way cheaper, only about 1 picojoule. So the cost of fetching and moving data is huge. So with that as a preamble, what the arithmetic costs, what it costs to move the data around, let's look at what precision we want to represent things with. Oh, and on the cost of moving the data around, one good way to think about this is that arithmetic units, let me go back to this chart, much like children and pets, are relatively easy to get. It doesn't take either much die area or much energy for the arithmetic itself. But they're very expensive to take care of. And that's really what this points out. You have to feed them with input data and do something with their output data and feed them with instructions. And the cost of taking care of your arithmetic units is far more expensive than the cost of the arithmetic units themselves. So let's talk about precision. Here is sort of the core operation that we want to do in a deep neural network. I want to take a weight ij, multiply it by input activation j, produce an intermediate product, accumulate that intermediate product, and store it as an output activation b. What I'm eventually going to converge on, but it's going to take me a while to get there, is that we can actually store our weights as 4-bit quantities using something called train quantization that I'm not going to get to until I get to the compression part of this talk, and decode them to 16 bits. What this means is that the expensive fetch of that weight only cost me 4 bits, a factor of 8 savings over a 32-bit weight. But I'm going to expand it up to 16 bits to actually do the computation. I'm going to store the activations in 16-bit form, do the 16 by 16-bit multiply, rounding the result to 16 bits, and then accumulate this sum to 24 or 32 bits before truncating it down to 16 bits for storage. And that way I won't lose any intermediate precision on the results. And I will point out that there's a technique called batch normalization, where as I compute a weight, I want to basically normalize that weight by adding an offset and multiplying, or excuse me, normalize that activation by adding an offset and multiplying by a scale factor, so I can sort of center that the range of that weight will be computed over a mini batch into the dynamic range of my representation. If I do batch normalization, I make much better use of the range of representation I have, whatever number system I use. If I'm doing training, in addition to doing the first part of that network, I basically take the input activation, the gradient, which I'm propagating back through my network. I multiply those And now I have the partial derivative that I want to accumulate for this weight. And I'm going to accumulate those, and I can multiply by a learning rate at some point in time. But I want to accumulate those into here. And the problem is, as I get further on with my training, this learning rate becomes very small. It might wind up getting to be 10 to the minus 5 or even 10 to the minus 7th in some cases. And so it's getting down to the bottom end of what can be represented in some of these number ranges. Recall that both 16-bit floating point and 32-bit fixed point only have about a 10 to the 9th dynamic range. And so if I have a really small learning rate, and the result of this computation winds up being small to begin with, if I use round to nearest in this computation, I will round my delta W to 0, and I will stop learning. I think this may explain what's happened to a lot of students that I've had in classes. So that you're actually, if you carried this computation out with unlimited precision, you would get a weight update. But because I am rounding to limited precision, and my update winds up being very small compared to the weight at late stages in training, it just doesn't happen. The delta W goes away. So the solution to this problem is something called stochastic rounding. In stochastic rounding, rather than round to nearest, I basically produce a result here to higher precision, and I basically round it up or down with the probability equal to its level in the range. So for example, if it's 10% of the way between number A and number A plus 1, I will round it to A with probability 0.9 and to B with probability 0.1. And so this actually is unbiased. It gives me the correct estimation, the correct expected value of the output. If I did round to nearest, I would always round it to the lower weight. And so if I do stochastic rounding rather than round to nearest, I get much better results, and I'll show you some data on that shortly. So for inference, how low can I cut the weight? So this is without doing the compression. This shows multiply energy on the left side for 32-bit and 16-bit, and I should have probably shown the 16-bit float for comparison, but it's about the same as the 16-bit integer. Remember that the energy doesn't vary very much float versus integer. It varies a lot, 32-bit to 16-bit. What you see is that our inference accuracy doesn't drop at all going to 16 bits. It drops significantly going to 8. So until I want to do some compression, 16 bits is kind of a sweet place to be for precision. This shows results with and without stochastic rounding. This is from a paper on deep learning with limited numerical precision, which I refer you to if you're interested in getting more data on this. It was at ICML this year. The black line here is using 32-bit floating point, so it's considered sort of the gold standard, the best that you can do. And then the blue and red lines are using fixed point 12-bit and 14-bit respectively. And the blue and red are with stochastic rounding. The tan and gray are without stochastic rounding. And what you see is that the training does not converge. It actually starts diverging after a while if you don't use a stochastic rounding with the lower precision. But with stochastic rounding, the 14-bit number is nearly as good. 14-bit fixed point number is nearly as good as a float. And actually, if you use 16-bit floating point representations, things are just really good because you have the dynamic range of a 32-bit fixed point number. So to sum up reduced precision, you can save all sorts of important things, memory capacity, bandwidth, power, and run faster by using smaller numbers. 32-bit floating point, it works great, but it's more expensive than what you need. Floating point 16 is just a really good choice in a lot of ways because it just works. It has the dynamic range of a 32-bit fixed point number, but you get a 2 times gain in memory and a 4 times gain in multiply power. If you're really careful, you can actually get things down to 8-bit weights for convolutions and 4-bit weights for fully connected layers, and I'll talk about that in the next section. If you do go to limited precision, 2 things are important. One is to make sure you center your activations in the dynamic range, and you do that by using batch normalization, where you basically learn over a mini batch a scale factor and an offset. So you basically land right in the middle of that range rather than being skewed to the upper or lower end of it and not using all of your precision. And the other is to do stochastic rounding, particularly during training where you get these really tiny weight updates. They will vanish with round to nearest, whereas stochastic rounding will give you an unbiased expectation of those weights, and you'll continue learning even after the weight got to a point where it would have vanished had you not been using the stochastic rounding. So next up is compression. And very often the cost of computing a network, whether it's for inference or training, is proportional to the size of the network. Particularly for unbatched inference, I at least have to read the whole model in, right? And so if I have a really big model, it's going to take a long time to read it in. When we put up on Archive one of our papers on compression, I got an email from Andrew Ng. It's like 3 days later, thanking me for it, for an application I didn't appreciate, which is for people who make mobile applications that they embed deep networks in. They have to be put in the App Store, the Play Store, and there's a limit on download to a certain number of megabytes. And if you can compress a network, you can basically put a much more robust network and still stay within the download sizes for these networks. So let's talk about how to reduce the size of our networks. So the first step is to prune the network. Much like you would prune a tree, you go into your network, and you say this network has too many branches, and you take your loppers and you lop a bunch of them out. As I'll talk about in a little while, this is actually a very old idea. The first paper I could find on it was by, of course, Jan LeCun with a paper called Optimal Brain Damage, which talked about the optimal way to prune your network. But actually, while it was a very active field of research in the late 80s and early 90s, it seemed to have petered out, and we kind of rediscovered it, and it works really well. So if I take, why did that not advance? Okay. If I take a network and prune it, you first think that I've destroyed my network. So in fact, if I prune it without retraining, depending on whether I use an L2 norm or an L1 norm, if I try to prune 90% of my network out, I've just destroyed the accuracy. I'm down almost 5% in accuracy at like 80% with an L2 norm. But the secret is to prune your network. And by pruning the network, what you do is you train the network normally, and then you apply a threshold operation. And every weight that's below a certain threshold, you simply remove from the network, and you make it so that it doesn't grow back. It does not, under subsequent training, try to increment itself. And then once that is pruned and you've destroyed your accuracy, you then run the training set by the network again with the constraint that you cannot add to the pruned things, and you get most of your accuracy back. And in fact, it does substantially better with an L2 norm than an L1 norm. And in fact, during parts of this, it actually has accuracy better than the original network. And then if you iteratively follow this procedure, so you basically prune, retrain, and then reapply the threshold, reprune and retrain, you can wind up actually doing substantially better, essentially taking across a really wide range of networks. These are results for AlexNet, but across a wide range of network, including RNNs for natural language processing, we tend to be able to get 90% of the weights out of fully connected layers without any loss of accuracy. So these are results for AlexNet. What you see is that while all the arithmetic operations are in the conv layers, all the weights are in the fully connected layers, and we basically get rid of 90% of those, so it winds up being 90% of the total networks. This shows by layer, whereby each layer 100%, how much we prune. What you notice is we can't take very much out of the first layer because you pretty much have to look at all the pixels of the input image. But once you start getting into the deeper feature detectors, you can prune 2/3 of them. You can get rid of 2/3 of the weights in most of the convolutional layers and about 90% of the weights in most of the fully connected layers. On VGGNet, very similar results. The convolutional layers get about 2/3 pruning. The fully connected layers, especially the really expensive ones, are actually able to get almost 95% out, 93% total pruning on the whole network. These are some results. I'll sort of go through quickly on pruning neural talk with a long short-term memory, so it applies to recurrent networks as well. What you see is you can prune up to easily 80–90% with no loss of accuracy. At 95, with the retraining, which is a green line, you start to get some loss of accuracy. And it's kind of funny to see. I should, by the way, acknowledge Song Han, who's my student sitting in the front row here. These are all his results. It's kind of funny to see what the loss of accuracy is. So pruning at 95%, instead of saying a soccer player in red is running in the field, it says a man in a red shirt and black and white black shirt is running through a field. So it's not completely brain dead, but it's just not as good or the same answer that it got before you removed 20%, or I should say all but 5% of its neurons. I don't think any of us would work as well if 95% of our neurons were removed. What's neat about these compression techniques is if you're in a situation where you can't batch, they substantially improve performance by simply minimizing the amount of data that you have to fetch. So these are results basically running a pruned network on both CPUs and GPUs. So the 1x here is a CPU running the dense network before pruning. We wind up getting, order of, if you look at the geometric mean bar here, order of 3x performance improvement on the CPU. The GPU, before doing anything, was actually 15 times faster than the CPU on this benchmark. And it gets about 3x as well. And then this is the mobile platform, which gets actually more like 4x on this. So again, the history of pruning, dating back to some work that Ian LeCun did in 1990 and lots of papers through the 90s. We by no means invented this. We kind of pulled this dusty one off the shelves and dusted it off to apply it to modern networks. And if you want to learn more about this, I will encourage you to see Song's poster tomorrow morning in C number 12. So now that we've pruned our network, let's talk about how to get rid of the weight storage. So the pruning you can think of as being this little flow chart here. Train the connectivity, train the network normally, apply your threshold, lop out the weights that are below a threshold, retrain the weights to learn your accuracy back, and then rinse and repeat. This basically gives us the same accuracy and reduces our size by tenfold. We get an order of magnitude size reduction by pruning. We now want to do less precision. So what we're going to do is, rather than linearly quantize the weights, when most people go to reduce precision, they basically say take a 32-bit weight and replace it with a 16-bit or an 8-bit weight. That implies a linear quantization where each bit represents a weight. The ith bit has weight 2 to the ith in an integer representation. We're going to do it differently. We're going to use the k bits of your weight to look up 2 to the k code words. We're going to generate those code words by doing a k-means clustering of the weights. That generates a code book, and then we're going to basically run the training set by and do backpropagation, compute the partial derivative of the loss function with respect to the code word, and update the code word to train our weights. It's a technique we call train quantization. We retrain the code book, and we wind up having the same accuracy, and we get not quite another 4x out in size. So we're down by, say, 35x in size. To give you an idea how that works, we're basically sharing weights. We start out and we train the network. All the weights are independent. We do a k-means clustering, and that basically clusters the weights into the blue, the pink, the tan, and the green weights. We force all of those weights now to have the same value, and we retrain the network to fine-tune the centroids on those weights. So with train quantization, you wind up with a distribution of weights that's shown with the red dots here. So if I have 4 bits, I get 16 weights. And you'll see that I've put the red dots where they do the most good. If I simply used a 4-bit integer representation, I would be sampling this space uniformly, which is the green x's, which doesn't capture the distribution as well. By the way, this is what a weight distribution looks like after pruning. The middle part here has been removed. That's what the pruning did. And it winds up not being a normal looking curve, but actually a bimodal distribution. If you apply this very aggressively with no loss of accuracy, you can represent the fully connected layers with 4 bits. This basically is bits going down, and actually the accuracy doesn't really fall off a cliff until you go from 2 to 1. You get remarkably good accuracy with just 2 bits per weight in the fully connected layers. The convolutional layers start losing accuracy at 8 bits and fall off a cliff later. And so there's a workshop poster on Thursday on this, and I'll encourage you guys to go see. Again, Song is the lead author on this. So I'm going to skip over some of these in the interest of time. Look at how I'm doing here. Actually, I think I'm doing okay. Let me go back to that. So we've applied this to a bunch of networks. These tiny Linnet is just a nice way of checking things very quickly. Essentially 40x compression rate on both the fully connected and the convolutional versions of Linnet. AlexNet 35x, VGD roughly 50x, and similar results for the neural talk, which is not on this slide. And basically, this is compressing things by pruning the unimportant connections, then quantizing the weight sharing. And then another step that I haven't talked about is after you've quantized, exploiting the non-uniform distribution of the weights with Huffman coding. So what does 30 to 50x compression of a network mean? Well, it means that you can put these things in mobile applications. I can take a really complex neural network for speech recognition or language translation, and I can download it to your phone because instead of taking 3 gigabytes, it's now 100 megabytes. And that's sort of the download limit. It reduces my memory bandwidth if I'm doing real-time applications where I'm batching, there's no reuse, and I've got fully connected layers. I just reduce the memory bandwidth, which is what is a real limiter in these networks, by 30 to 50x. And a real multiplier that I'll talk about even more when we talk about fixed function hardware is I've reduced the size of the working set by 30 to 50x, which means for a lot of working sets it will now fit in on-chip memory instead of having to be in DRAM. And so remember that order of magnitude cost differential from going from local memory to distant on-chip memory to off-chip memory. If I can pull in through one of those levels, there's another order of magnitude of efficiency to be had. So before talking about fixed function hardware as a hardware designer, which is sort of near and dear to me, let me talk about better algorithms. This will be sort of a short section, but it's an important one because I've seen a lot of people accelerate the fixed function hardware, but do it with the slow algorithms, and they actually wind up being slower than running on general purpose hardware using the fast algorithms. So my mantra here is if you're going to accelerate something, make sure you start with the fast algorithm, because a better algorithm will trump better hardware all the time. I hate to say that as a hardware guy. And so for convolutional neural networks, we spend the bulk of our multiplies in the convolutional layers. In fact, it seems to be all the rage these days to sometimes just get rid of the fully connected layers and do everything with convolutional layers, as with GoogleNet and the Inception architecture. So if you're going to be doing convolutions, the right way to do a convolution is with a transform. Remember, the complexity of doing a convolution, if I do it brute force, is k squared, where k is the size of my kernel. If I have a k squared kernel, I need to basically multiply every element of that kernel by every element of the window to produce 1 pixel of output. So for every pixel of output, I do k squared multiplies. If on the other hand, I apply the basic theorem that we all learned when we were sophomores in college, that if I do an FFT and a pointwise multiply and an inverse FFT, that's a convolution. I can basically reduce it from a n squared computation to an n log n. But the n here now is the size of the whole image. You think that that's a really bad idea. You can tile the image and play with that. But the thing that really makes this work is the fact that I'm not doing it once, right? Let's look at the inputs, because they're the ones I'll be doing over and over again. For each of these inputs, I have to compute not 1 output channel, but say 256 output channels. So if I pay the n log n computation to apply an FFT to each input image, I get to reuse that transformed input image 256 times, once for each output image. And similarly, I now have to do the inverse transform for the output images, but I get to do that for each of the input images. And so I get to sort of amortize the cost of the transform over the fact that I'm doing this convolution for every input image times every output image. So the way to think about this is that if I have k input filters and j output filters, I basically get to do the transformation once and then reuse them k times for the input and j times for the output. So I'm amortizing those FFTs over k input maps and j output maps. So a conventional convolution, I basically do k times j, that's all pairs, input to output maps, times m squared, where m is the size of the convolutional kernel, I'm assuming it's square, times n squared, once for each pixel of the output map. For the FFT, I do the 4kj n squared. That's basically doing the pointwise multiply. The 4 really I can reduce to 3 is the cost of doing the complex pointwise multiplication. And then I have this thing which is n log n, but it's multiplied by k plus j instead of k times j. So if I have hundreds of filters, this term goes away, and I basically have reduced an m squared computation to a computation with 1 complex multiply per point. So the paper here by Mathieu et al. in 2013. It sort of has the data on this, and this is their result out of the paper, showing speedups even with 3x3 kernels. With a 3x3 kernel, this is about twice as fast as doing the brute force convolution, and it gets better from there. And in fact, what you see is the cost of doing a convolution with FFT is independent of your kernel size. I can do a 13x13 kernel with exactly the same cost of compute as a 3x3 kernel. And so what I suspect is, as people move to doing FFT-based convolutional kernels, they will go back to using larger convolutions, whereas there seems to be a trend to push everything down to 3x3s and 5x5s today. The other fast algorithm I wanted to mention, and I won't spend too much time on it, is Winograd's convolution. And this goes back to a paper in SIAM in 1980, and more recently in this paper by, the thing is covering the author's names, it's a recent paper on fast algorithms for convolutional neural networks. And it's basically the same thing as the FFT, but a different transformation that's actually based on thinking of the convolution as polynomial multiplication and then applying the Chinese remainder theorem to the polynomials. Whenever I try to work the math out, it makes my head hurt, but you don't actually have to work the math out. You just find a library that does it. And so basically what you're doing is the same thing. The U and V here are the kernel and the input image transformed by the forward Winograd transformations. And then the A, the application of multiplying by A and A transform, is the inverse transformation. And what it does is, again, it reduces, you can amortize the cost of the A, which is transforming the output image, the cost of transforming the input image in the kernels over the fact that you have many input channels and many output channels. And it basically reduces, again, this sort of k-squared computation to do a convolution to being a single real pointwise multiply as opposed to the complex pointwise multiply for the FFT. So to sum up algorithms, and I wanted to do this before getting into the hardware part, because you'll see how a lot of the conventional hardware, or I should say special purpose hardware, has dealt with this. If you do an FFT or Winograd convolution rather than a regular convolution, you're basically 2 times faster if you're doing 3x3 convolutions, and it just gets better. With FFT, you're about 25 times faster on 11x11s, which are, for example, part of the first stage of AlexNet is an 11x11. So special purpose hardware running a brute force convolution is slower than a GPU running a transform-based convolution. And what's really great about the FFT convolutions is they're independent of convolution size. It costs no more to do a 5x5 or 7x7 or even a 11x11 convolution than it does to do a 3x3 if you're using an FFT to do it. Okay. My second favorite topic after GPUs is hardware for deep neural networks, because I'm fundamentally a hardware designer and I like building widgets. And many people have been building widgets for deep neural networks, but I'll preface this section by saying that they hold great potential in special circumstances, but for 90% of the applications of neural networks, you're better off with the GPU. With that preface, let me dive in and talk about fixed function hardware. To be maximally efficient, you're better off with fixed function hardware unless you're memory limited. If you're doing a batch 1 neural network where you have big fully connected layers and you're fetching those parameters from DRAM, I don't care how you do your arithmetic. Your energy and your time is going to be completely limited by your memory system, and you'll do no better than a GPU memory system. They're very highly tuned. In fact, most fixed function hardware won't match that because their memory systems aren't as good. But if you're not memory limited and you aren't going to be changing your algorithm anytime, I mean, somebody publishes a paper in Archive next week, and your chip hasn't even come back from fab yet. That's too bad. You're fine. So people have been doing this for a while. A piece of work that got a lot of attention when it came out at ASPLOS in 2014, so it's February 2014, was DNN, which my Chinese-speaking graduate students inform me means electric brain. So I want to know where I can get one of those. And it basically has a dedicated function unit for doing the multiplies and then summing the additions for both the fully connected and convolutional layers. So it has 16-bit integer multipliers and 16 of them, and then a summing tree to produce the one activation. it has relatively small buffers for the weights and the activations, and a small output activation buffer. So it requires going out to DRAM to fetch everything, but if you're batching, it can get a certain amount of reuse out of this. And they basically show some results here in, I believe it's a 65 nanometer process, getting reasonable results in performance per watt. So 452 gigaops at a half a watt, so it's about 1,000 ops per watt, 16-bit fixed point. This same group, which is a collaboration between folks at INRIA and Chinese Academy of Sciences and Tsinghua, went on to do DNN now, which means bigger electric brain. And what they did here is realize that they were limited by their memory and chose to put a bunch of memory on their component. So they have embedded DRAM on this part. The part is basically a big memory chip. These are all the memory components, and it's tiled. So you have some of the memory and then a compute unit for each of these tiles, and then the function unit so basically sits in the middle of each of them. And it basically can hold 12 million parameters and can consume 16 watts. And so if you have a model that fits in 12 million parameters, this is great, because now all the fetches are entirely on-chip. You avoid, you're basically getting global on-chip references at sort of 50 picojoule per word, not having to do the 640 picojoule per word for going off-chip. And they also published in ISCA this year, DNN now, which means vision electric brain, which is really sort of specialized to the convolutional layers. Earlier at ISCA, and I believe it was 2012, somehow the date got dropped off of that reference, there was the convolution engine paper published, which basically shows how even if you're doing the brute force algorithm, you can basically reduce your energy by building a fixed function piece of hardware that kind of maximizes the weight reuse and activation reuse of doing a convolution. But again, this is doing the k-squared convolution rather than a transform-based convolution, so it's doing k-squared too much work. And of course, it's always been published first by somebody in Jan LeCun's group. He has a paper on NewFlow, which is an implementation of doing neural networks and other vision algorithms where they implemented 150 GOPS thing in an IBM SOI process. Recently, some work by my student Song looked at how we could take our compressed network and accelerate it, because the problem with a lot of these previous networks, probably the best of which is the DNN now, are limited by having to fetch all of their parameters from off-chip. DNN now overcomes this by having on-chip EDRAM, but it can only hold 12 million parameters. And you can cascade these chips together, but to hold a 100 million parameter model, you need 8 of them. It gets a little bit unwieldy. We chose to look at how we could take these compressed networks and deal with them. So with the compressed networks, even without EDRAM, we're able to take a pretty sizable network and hold these sparse matrix in on-chip SRAM. And these sparse activations are actually held in pointers that are in this arithmetic section here. These are the destination activation pointers and the source activation pointers. And by storing the matrix in a compressed sparse column format rather than compressed sparse row, we're able to exploit the dynamic sparsity of the output activations by doing a distributed find first non-zero. So we basically, in a distributed manner, find the non-zeros in the input activation, broadcast those to all of these tiles. Every tile multiplies that activation by its portion of the column that's non-zero, basically using the sparse matrix representation to skip over the zeros without having to visit them, and then updating those. And then you switch the input and output activations for the next layer. The speed-ups here have been really good. And again, the first parts of these I've already showed you about. These are the speed-ups of just compressing on the CPU and the GPU. What you see is you can go even faster than the GPU. The geometric mean number here is about 180 x. What happened to my mouse? You can't see this off the screen. Up here, there it is. About 180 x. And that's because you're able to keep this entirely. It's really a question of locality. Here we're keeping it not just entirely on chip, but all of the data is being fetched by SRAM sitting right next to the arithmetic unit, so it's down in that 5 picojoule bin. And for that reason, the energy efficiency is much larger. It's actually 24,000 times faster than the CPU, more energy efficient than the CPU. Again, I've lost my mouse. There it is, okay. that's the number over here, 24,000 times faster than the CPU. And you may basically have me in disbelief at this point and think that I've cooked the books, but you can actually multiply the numbers together and see how I get to this number. I first of all have pruned the network by about 50x. So I save 50x by only having to fetch 1/50th the parameters. Then for the fully connected layers, which is where a lot of the density comes from, I'm doing a 4-bit representation. So I get another reduction in energy by not doing the 32-bit floating point. And then I get this 120x advantage by being able to fetch my parameters from on-chip SRAM at 5 picojoules per bit, rather than from off-chip DRAM at 640 picojoules per word. And that winds up giving me, if you multiply them all together, it actually comes up to higher than 24,000. And the reason it's only 24,000 is that this is implemented in a 45 nanometer process. It's about 6 generations back. It scales well. This basically shows as you go from one processing element to 256 processing elements, how the performance scales. Some of the networks start topping out at around 64. Most of them scale pretty linearly up to 256. And I should say this is strong scaling. Even for the big layers here, a lot of the VGG layers, they're 4K by layers. But with 256 neurons, you have 16 activations per PE. But remember, our density here is about 10%. So you actually have 1.6 non-zeros per processing element, and you're still getting very good speed up, which just shows that if you can eliminate a lot of the overhead, this has been very highly engineered to have very efficient communication and synchronization, you can exploit the parallelism down to single operations. And that's in fact what's going on when you scale this to 256. No talk on special purpose hardware for deep learning would be complete without talking about GPUs. So you have to realize that this is the CTO of a GPU company telling you about FPGAs. But I'm trying to be entirely factual here. So the facts are what an FPGA is a field configurable ASIC. All the things I've showed you so far, the DNNs, the new flow, the convolution engine, our efficient inference engine, are all ASICs, that is application-specific integrated circuits. The great thing about an ASIC is you can build hardware to do exactly what you want, get rid of all the control overhead, and it's great, except the cost of doing an ASIC these days is around $50 million to get the first copy. In fact, whenever I talk to people, they think I'm being optimistic. Many people would use $100 million as the sort of engineering and tooling cost to build an ASIC today. I actually have done several startups in the past where our business plan was to build special purpose ASICs. And nobody does those anymore because the cost is just too high. You just don't see them anymore. Instead, if somebody has a piece of hardware they want to prototype, they'll build it on a field programmable gate array, an FPGA. And there's good news and bad news about FPGAs. The good news is that they have a bunch of fixed function logic on them. In the early days, in the old 4000 series Xilinx parts that came out in the 1980s, I was a professor at MIT at the time, and I converted our undergraduate logic design course to use FPGAs. And all you got on the FPGAs were what were called LUTs, lookup tables. So you could implement random logic using four input arbitrary function gates. And today, in addition to those, you have fixed function integer units, floating point units, and memories, and and even ARM cores on some of them. And those fixed function units are great. They're as good as what you get on any other chip. The problem is whenever you need logic that's not on those fixed function units. If you build logic using the LUTs, and it's not hard to understand why this is the case, if I build, say, a 4-input AND gate on a real ASIC, it's going to be about 8 tracks in one direction by 10 tracks in the other direction. And a track these days winds up being about 1/10 of a micron. So a 4-input gate in an ASIC is about a micron by a micron in size. If you look at the way that the LUTs are implemented in an FPGA, it winds up being like 100 microns by 100 microns. So in area, you're off by about 10 to the 4th, and it winds up being that in sort of energy and speed, you wind up being about 1.5 to 2 orders of magnitude off. We've actually done some prototyping studies, and it wound up sort of with the FPGA typically being about 100x worse than the ASIC for anything that doesn't actually fit into the fixed function units. And so this usually winds up being sort of the demise of ASICs, particularly if you want to do some things like reduced precision. The recent area and Stratix parts from Altera, now Intel, for example, have 32-bit floating point units, but they don't have 16-bit floating point units. If you wanted to reduce precision and do 16-bit floating point, you'd be down a factor of 100. You're better off doing the 32-bit floating point. Even some of the most ardent proponents of this, which is the people from Doug Berger's Catapult group at Microsoft, have data that basically shows that they're not really that competitive. They're better than CPUs, although this number is kind of low for CPU. My number would be higher. This is basically GOPS per joule on the CPU, on the FPGA, and on a Titan X. And also, I don't know why they're charging a Titan X with 475 watts. It's a 250 watt GPU, and that counts the voltage regulator and the RAMs. But even so, it's on the order of a factor of 8 more efficient. This is from a presentation that Microsoft did at Hot Chips this summer, and this was presenting their real results. The next two slides are hand-wavy slides showing that in theory they should be doing much better, but they aren't. This is what they're doing. Short on time, so I'm actually going to sort of quickly skip over this, but this is sort of similar results from a bunch of different FPGA projects on various Xilinx FPGAs. And what you see is that the GOPS per watt numbers come out in about that range. This one actually winds up doing a little bit better, and there's some reasons for that. So let me sort of wrap up the hardware comparison with a table and then some bullet points. So in the table, I'll compare a Titan X, a Tegra K1. These are some of the Song's results, and I haven't been able to get him an X1 yet for some reason. An FPGA, which is AI, which was one of the ones in the previous slide. The DADian now, that's the bigger electric brain, the one with the on-chip EDRAM, and then our efficient inference engine. And if you look at how it does on the whole operation, the real winner here is DADian now, because for the convolutional stages, it can sustain very high GOPS per second. But if you wind up having to implement some fully connected layers with a batch size of one that don't fit on chip, you quickly wind up down with this efficiency for matrix times vector, and we wind up doing a lot better with the efficient inference engine. Even so, that winds up in GOPS per watt, doing quite a bit better than you'll do on the GPUs. So there is advantage to fixed function as long as you're not limited by memory. So just to sum up, we looked at a bunch of fixed function units, the various electric brains, the convolution engine, and our efficient inference engine, which is really designed to directly execute pruned and compressed neural networks. And it does that in a way that does no data movement, so you're fetching everything from local. The bottom line is that the arithmetic performance per watt of special purpose hardware winds up really being about 2x a GPU. So if I look at the numbers of what we get on a Tegra X1 running FP16, basically half of our energy is in the FP16 units. And therefore, if you eliminated all the overhead and you were doing FP16, you could get 2x out of fixed function hardware. If you're memory limited, you're no better than a GPU, because your memory, if you have to fetch from off-chip memory, you're basically limited by that off-chip memory, and you'll do no better. The big win from special purpose hardware is when it's a special purpose memory system. This is the case both for the DADian now and for our efficient inference engine, because if you can get the entire model to fit in on-chip memory, then you do substantially better, because you're basically eliminating that expensive memory fetch from off-chip memory. And decompressing highly compressed networks requires a lot of irregular operations. If we're representing the weights by 4 bits, there's bit manipulation to extract the 4 bits you want, a table lookup to look up the code word and decompress the code word. That stuff runs really well on special purpose hardware and not so well on CPUs and GPUs. So there's a big win for the special purpose memory system for the decompression, not so much for straight arithmetic. GPUs are within about a factor of 2 on FP16 for the straight arithmetic. FPGAs are just inefficient ASICs. They're great at arithmetic and memory. They're really bad when you've got to build things out of the LUTs. which also includes things like decompressing the networks and doing other than the standard arithmetic operations that come built in. So we're getting toward the end. I see everybody looking at me as if I'm the only thing standing between them and dinner. So let me get to the summary part, and then perhaps we'll have time for a few questions at the end. So to go back to where we started, the current revolution of deep learning is very exciting, and it's being enabled by two things. One is lots of data, and the other is really fast hardware. It takes both to make neural networks work. A lot of the basic technologies were around in the 1980s. We didn't have either the data or the fast GPUs until today. In 1990, a CPU, so when Jan LeCun wrote the original convolutional neural network paper in 1989, a single CPU had a spec-int score, a measure of performance, of 100. Today, that CPU has a spec-int score of 30,000, and you can get 6 to 8 or even 16 of them on one chip. So that gives you 200,000 times more performance on one CPU chip than you got with an Intel 486 in 1989. There are very few other endeavors of human beings that have had a 200,000 times increase over any period of time, let alone 15 years. But it was a really good ride while it lasted, but it's over. I mean, the Moore's Law charts are flattening out. We're not going to get that increase of performance from process scaling anymore. The way we're going to get it now is sort of through cleverness of various kinds. The first kind of cleverness is to move to a GPU, which will give you about another 5 to 10x. So instead of 200,000 times our machine from 1990, we're going to be 2 million times. And again, the reason why GPUs do so much better is that they're just very efficient parallel execution engines. We hide the unpredictable latency of cache misses, not by having complicated out-of-order scheduling hardware as a CPU does, but rather by multi-threading and just switching threads, which is very inexpensive. And we can basically be comparing the TX1, which is only one generation of technology back, to a Core i7. One generation of technology back, it's 11.5 times as efficient. You can then get another factor of 100 by exploiting parallelism on the GPUs, as Baidu demonstrated with their deep speech 2, scaling from 1 to 128 GPUs with linear speed up. If you really want to go faster than that, you can then get about another factor of 100 going to special purpose hardware. But it doesn't come from hardwiring the arithmetic computation. It comes from getting the working set of memory on chip, because that's what gets me that 120x difference of 640 picojoules fetching a weight from DRAM to 5 picojoules fetching it from a local memory. And it comes by hardwiring the decompression of the compressed network, which is a very irregular computation and isn't as well matched for CPUs and GPUs. So this is the point in time where the good Dr. Daly is going to do a prescription. So basically the starting prescription is accelerate the best algorithms, prune the network, compress the network, and FFT the convolutions, or use a fast algorithm for the convolutions. And then you're up sort of 25 billion over what could be done in 1990. So here's the prescription. What should you do to have high performance hardware for your favorite neural network? So if you're training, use a cluster of 8 to 16 GPUs. There's nothing that even begins to compare to that now. I think that if I were to build special purpose hardware for training, I could probably do a little bit better. But by the time I got done, there would be a new generation of GPU that would probably be better than my hardware. It's the best performance per watt, the best performance per dollar. And because the modern GPUs have 300 gigabytes per second of memory bandwidth, for the cases where your memory bandwidth limited, that they're just unparalleled. Actually, once we move to stacked memories, we'll have a terabyte per second of memory bandwidth on our GPUs. And the parallelism is easy. And I should say the programming is easy too, because all of the standard packages, Caffe, Torch, Theano, all have GPU-enabled packages in them. If you're in the data center doing inference, use a Titan X, or the Tesla is our data center brand. They're sort of made more reliable, more suitable for data centers. The M40 is basically a Titan X in a more reliable configuration. The M4 is for an observation that many people in a data center don't have a PCIe slot provisioned with 250 watts. which is what a Titan X needs. So the M4 is a 75-watt GPU set up for the data center and can be operated anywhere from a 25 to 75-watt power envelope for power-limited data center applications. And so a lot of people have already deployed a data center. They've got 50 watts in a PCIe slot. They can now get way better performance putting a 50-watt M4 into that slot. If you're building a self-driving car or you want your toaster to be smarter, I can't quite understand how my toaster can be smarter than it already is. But if you basically want to put inference in mobile devices, what you really want is a Tegra SoC. It's 11.5 times the perf per watt of a CPU. It's kind of the right form factor for Internet of Things and for automotive. And if you want the absolute best performance and efficiency, use an ASIC. But your model better fit in the on-chip memory, or you're basically going to be no better than a GPU because you're going to be memory limited, and your power and performance is going to be completely limited by that memory interface, and that's going to be the same as the GPU. And use the best algorithm and make sure it's not going to change, because if somebody publishes a great paper on arXiv next week and your special purpose hardware can't do that, you're going to be really bummed. So with that, let me thank you, and I probably have 7 minutes of time for questions.
Okay.
By the way, before questions, I should ask Song to stand up. Song did all the heavy lifting and everything I talked about, and I just got up here and talked about it. So. He'll be graduating in about a year, but I'm going to try to hire him at NVIDIA.
Romain?
Thank you, Professor, for your intuition. I had one question. I was wondering if maybe you could elaborate on your intuition behind why exploring larger convolution size will happen after we start using FFTs to do all of our convolutions. Is there any specific reason for that?
Oh, that's a really good question. So the question, I guess everybody can hear since you have a mic. The question is, why do I think people will move to larger convolution size once we're using FFTs for convolution? And the reason is it's free. And so having a larger convolution can't hurt because if the right network was to do a 3 by 3, you would train the 10 by 10, or actually you probably want it outside, the 9 by 9 convolution, and it would be all zeros except for the 3 by 3 in the middle, right? But if there's some value to having those weights further out have non-zero values, then it doesn't cost you anything. It's free. You might as well use them. So if it's free and it does more, I imagine people will do that. There's a trade-off between the size of the convolution and the number of convolutional layers. And you need a certain number of convolutional layers, a certain amount of depth to get enough nonlinearity in your function. You can't do it all with one convolutional layer because that will only learn linear things. You need to have convolutional layer, nonlinearity convolutional layer to be able to get nonlinear feature detectors. And so you need some number of layers. But once you have that number of layers, you can get a much bigger receptive field by making the individual convolutions in those layers larger, and it doesn't cost you anything if you're doing an FFT convolution.
Do you mind if I go with a follow-up? Really
Sure.
quick, sorry. What I was going to say is that framework at all amenable to variable size convolutions in the same kind of architecture?
Yeah, certainly, because once you're doing the transform thing, what you typically will do is you'll tile the image, and then you'll transform both the kernel and the input map to the tile size. So you can do the pointwise multiply at the tile size. And so you could make the convolutions between layers variable size, or even within a layer, if you basically switch parameter sets on different fields of the layer, you could use different size convolutions.
I have a question about pruning.
Okay.
So when you have before pruning, the connections are implicit. You don't need to have a list of all connections because you have convolutions. But once you prune, does that mean that now you need to also store somewhere in your memory the explicit list of
yeah, it's a great question. So the pruning results I gave all include the overhead of representation for the sparse matrix. So when you have a dense matrix, all you have to do is remember the weights because it's implicit where they are. If you have a sparse matrix, you typically store it in a certain format. And the format we use is the compressed sparse row format. Let me find the, it's actually easiest to show you the hardware picture. Overshot. Well, that's interesting. Get my family picture up there. Beautiful family. In the compressed sparse row, we use a compressed sparse column format. We store a pointer. So we have a big array of non-zeros, and then we have a big array of how many zeros are between the non-zeros. And we have a pointer to that pair of arrays. They're one-to-one, so we only need one pointer for every column. So that basically says where in the array that column starts, and then we basically have, in addition to the weights, the spacing to the next weight. And so the overhead, if you're using 32-bit values, is basically about 4 bits per 32-bit values, like 12% or something. Once we condense down to 4 bits per weight with the quantized training, the overhead is 100%, but all of the compression results that I gave you include the overhead for the sparse matrix representation.
But does that mean you can't do your FFT because now your receptive field has holes in it?
Yeah, so that's a really good question. So if you're going to do an FFT, you have to first expand it out because the FFT algorithm requires dense elements, a dense algorithm.
Okay, thanks.
And actually, at a certain level of sparsity, you'd be better off just doing the DFT.
Thank you for the talk, Professor. A question on using the FFT in the kind of the energy hierarchy. Moving data around is bad, computing is good.
Yeah.
As you illustrated on your slides. To get the benefit or the power with FFT, we really need to have a fair amount of input and output feature maps. That way you're minimizing the overhead from the transformations to the spatial and back.
That's right, yeah. You're amortizing the transform over the number of maps.
Exactly. So, but the total number of feature maps you have is the product of input and output feature maps, and the size of the FFT maps that you're using is actually larger. So you end up having to have a lot of feature maps that end up being larger in size than the original kernels that you had if you were just doing the brute force convolution.
Yeah, that's
How does
really
that balance or shake out in the
Yeah,
total?
so that's a really good question. And that's the reason why, even though sort of the way this is illustrated, it sort of shows the kernels and the input feature maps being expanded up to image size. You typically don't do this at image size. You typically tile your FFTs. And so you'll take your image and you'll tile it typically only slightly larger than the FFT kernel. And then you'll take the tiles with overlap to account for the FFT kernel, and you'll take those tiles of input image and those tiles of kernel, and you'll transform them. And because the dilation is relatively small, it does increase your storage slightly compared to just storing the kernels and the input maps. But depending on how you choose the tile size, it's perhaps maybe 2 or 3x. It's not an enormous.
Yeah, I was just thinking for like a tile size of 16 by 16, which for small feature map sizes and 3 by 3 kernels is reasonable. You're kind of going
you may not want to go that big.
Well, okay. Yeah, I was thinking from that you were going from 9 to 256, but I guess if you're going smaller.
Yeah.
Thank you for coming. I just wanted to ask about when you're training these networks using very, very dense matrices, and then afterwards trying to sparsify them, it makes me think that really what you're doing from the very beginning is trying to phrase this as some sort of lasso problem where you want to find a very sparse solution in the first place. And I was wondering if you know of anyone that has any success, or if there's any work that would be good in doing in making a lasso problem of the neural network training.
So I didn't quite, you said a something problem, but basically you're talking about the problem of finding the sparsity directly rather than sort of training it densely and then pruning it out.
Yeah, almost more like as if you're trying to find, say, a sparse inverse covariance matrix and use some sort of iterative shrinkage algorithm.
Yeah, no, I've surveyed the literature a little bit. I wouldn't say it's been exhaustive, and I've not found anybody who's done that. I wish they would, because it would make it faster. Right now, probably the one weakness of the prune networks is that it's a longer training process. You have to train the network to begin with, and then prune it, and then train it again, although that second training is much quicker.
Again, thank you so much for the systematic approach to improve DNN. This is great mind-blowing. I'm Jen Li from Huawei Technologies. We actually have been doing that in this area, but I want to understand your opinion, your guidance here. Let's say we start from 128 GPUs. So you talk about memory and network overhead. We all know you are the network experts here. So let's say we pick three kernels, LU, convolution, and the weight updating. You mentioned weight updating, you mentioned convolution. Now between the three kernels, which one, when we go beyond the current shared memory or direct memory access clusters, which one could be more like network intensive?
Yeah, normally people will only employ model parallelism within a cluster just because you've got to move so much data around, and you can do clusters of up to like 8 or 16 where you're sort of directly writing the memory of the remote GPU. And then if you're going to go above that, people will normally use data parallelism. And with data parallelism, the only thing that you really need to exchange are the weights. You basically, after each mini batch, you have to basically transmit the delta weights around so that everybody sees every delta, either by sending up to a parameter server and back or by just circulating them around all the workers. So it's typically data parallelism that you use at the outside level.
Yeah, but when we go beyond larger networks, right? I'm just, I guess I'm making it up now. If we have a cluster over 128 GPUs, would LU be a problem there? Because LU can be very network intensive.
When you say LU, you mean like basically doing the matrix vector multiply.
Right, right.
Yeah, but you won't do that over the network, right? You'll do that entirely within one cluster of GPUs. Any model decomposition will be entirely local to the cluster, and the parallelism you'll get across clusters will be basically data parallelism, where you're running separate models on different subsets of your input set and exchanging parameters.
Okay, thanks.
Yeah.
Hi, thank you for the presentation. It was really interesting. I have two questions. One is about this slide. I guess there is a typo. It should be n squared and logarithm n. Isn't it?
Yeah, it should be n squared logarithm n squared. That's, hold on a sec.
Okay, thank you.
Yeah,
Now
sorry
I
about
understand.
that.
And one more question. You had a plot where with x-axis there was number of GPUs and y-axis had number of seconds, and there was a point that had 10 to 18th power of seconds. How is that possible? How could one measure such a
Oh, so what was the chart? Was this the Baidu one?
There was a linear curve, and y-axis had 10 to 18th power of seconds.
Yeah, no, so since 10 to the 18th power of seconds is probably something like 100 years, they clearly didn't run that long. I think they did an estimate running a small part of the computation and extrapolated how long it would have taken had they used just one.
Actually, all the values in the y-axis were very large.
Let me find that. This was the Baidu chart. We got some real fact-checking sort of people in here. Oh, it's 2 to the 18th. Is this the chart you're talking about?
Could you please show it? Oh, yes, it's it.
Yeah. So you're just using a different radix.
Sorry?
Yeah, I believe they actually did those runs too. So 2 to the 18th would be something like 10 to the 15th seconds.
So even, I don't understand, the smallest value is, oh, it's 2 to 18.
Yeah.
I see. Okay,
Yeah.
thank you.
Yeah.
The stochastic rounding technique that you described earlier reminds me a lot of simulated annealing, in that the limited precision computation has the effect of sort of introducing artificial local optima that the addition of noise escapes. So I was wondering if anybody has actually thought of the problem in this sense, and if some of the results, the classical results from simulated annealing about temperature scheduling and convergence rates do apply.
Yeah, that's an interesting observation. There is that probabilistic sense to it. I should probably go back and read the paper and see if they mention that. I can't recall. It's been a while since I've read that paper. Okay, are we done?
Okay. So thank you very much. Let's thank Bill.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.